Hello everyone, my name is Jason Gregerson. This video is going to be on equations of lines. Consider the line that contains the point 0, 2 and has a slope m equals -1/2. We can use the slope-intercept form of the equation of a line, y equals mx plus b, to write the equation of this line, y equals -1/2x plus 2. And so we'll talk about that being the equation of this line, but really we should recall that the definition of this line is the set of all points like x comma y, that satisfy this equation. So I could ask, is this point 0, 2 really on the line? And to answer that, I would plug in x equals 0 and y equals 2 into my equation and see if I get a true statement. So with that in mind, if we want to find other representations for this line, really we need to think about other ways we can represent all of the different points on this line. So today we're going to look at how we can do that with vectors. So I have the point P, which is the point 0, 2, and I'm going to come up with a vector r sub 0 that's going to be the vector that goes from the origin to this point. So I'll draw that guy over here. That's going to be my r sub 0, and that's going to be the vector 0, 2. And I can really think of that vector as representing one of the points that's on that line. And now if I want to represent a different point on that line, this point over here, I could think about the vector that goes from P over to that other point, and that vector is traveling in a certain direction, the direction that the line is going. And so how do I find that vector? I'll call that vector V, and it looks like to get from one point to the next, I'm going to go over 2, down 1. And that makes sense with my slope of -1/2. I'm going over 2, down 1. So that vector v is going to be 2 in the x direction, -1 in the y direction. So now I have this vector representation for the direction of my line. And so I can see that this point that the second point on the line, I can really represent as r0 plus the vector v. And that terminal point of the sum of those two vectors is this point that's on the line. So I have r0 plus v. But then what if I looked at r sub 0 plus 2 times the vector v? How would that change things? Well, I'm just doubling the length of v, so that would give me a vector twice as long. And that terminal point of that sum would still be another point on this line. And if I change this to 3 times v, I would just get a new point on that line. And so what I can see is if I take r sub 0 plus any number times the vector v, I will find a new point on this line. And therefore I can write this equation, r sub 0 plus t times v, and that would represent all the different points on that line. And this is going to be our vector equation for this line. Now, why do we care about this vector equation? Well, one reason is because we can generalize things in 3 space using these vector equations where we can't using our regular equation that we're familiar with. What would that look like? Well, consider this problem. Find a line in 3 space now that contains the points 0, 0, 3 and the point Q, 1, 2, 0. Now we have this picture all drawn up, so we have our point P right here and our point Q, and so we can see our line going from P to Q. And I can really just use that same vector equation for my line. R sub 0 plus t times my vector v. And I don't care whether these vectors are 2-dimensional or 3-dimensional or 4 or 5-dimensional, whatever that would look like. I just have to find these vectors and I'll find the equation for this line. So in this case, r sub 0 is just the vector that goes from the origin up to my point. And so that's just going to be the vector 0, 0, 3. And now I need the vector v that's traveling in the direction of my line. That's going to be the displacement vector that goes from P to Q. So to find that vector, recall that I will just subtract the component values of my 2 points. So I'm going to take this x value minus this x value. I'll get 1 minus 0. Similarly, I'll get 2 minus 0 and then 0 minus 3. And so I have v as the vector 1, 2, -3. And as soon as I write out that vector, I should also just give it a quick check to see if it makes sense. This vector tells me that to go from P to Q, I'm going to travel 1 in the x direction, 2 in the y direction, and -3 in the z direction. So yes, that does describe me going from P to Q. And then all I have to do is put everything together. Looks like my equation for this line is going to be r sub 0, or 0, 0, 3, plus t, some number, times v, which is 1, 2, negative 3. And now I have my equation for this line in 3 space. So we can also generate a couple more other representations for this line, but the first question would be why? Why do we care about other representations? Well, we've actually experienced this before. We've looked at y equals mx plus b and said, okay, if I know what the slope is, I know what the y-intercept of a line is, then this is a great equation to use because I can just plug in my values for m and b. But what if I don't know the y-intercept? What if instead I have just some point that's on my line, not necessarily the y-intercept, but just some general point and the slope? Well, then I can use the point-slope form of the equation. Y minus y sub 0 equals m times x minus x sub 0. And of course, if we looked at this point-slope form and we looked at a specific point that was 0b, was the y-intercept, and we plugged that into point-slope form, it would give us exactly the other form. So really, these equations are the same thing. They're just algebraic manipulations that bring us from one to the next. But they're useful for specific problems. And it's going to be the same thing with these other equations for lines. So we have 3 different representations. We have the vector equation that we looked at. We're also going to talk about a parametric set of equations and symmetric equations. And what I want to stress here is these aren't 3 sets of representations for lines that we have to memorize, but it's just little algebraic manipulations that bring us from one to the next. So, for instance, we know our vector equation. This is saying that to find the terminal value here, this x, y, z vector, we're going to take r sub 0, which is some initial values, x sub 0, y sub 0, z sub 0, plus t times our direction vector, which I'm just going to call a, b, c as just the components of that vector. Well, we know how to multiply vectors by scalars, and we know how to do vector addition. So we could simplify the right-hand side of that equation as x sub 0, this x component, plus t times a. So plus t times a, which we could also write as a times t. And the rest of this vector would be y sub 0 plus b times t, z sub 0 plus c times t. And this is still equal to x, y, z. And of course, these two vectors are equal if and only if their components are equal. So that means x must be equal to this piece, which is exactly our first equation from the parametric set of equations. And so we can see that this is how we get that parametric set of equations. What about the symmetric equations? Well, to find the symmetric equations, all we're doing is taking each one of our parametric equations and solving it for t. So in the first case, if I'm solving x equals x sub naught plus a times t for t, I'm going to take that x, I'm going to subtract off the x sub naught, I'm going to divide by a, and this is what's equal to t. Well, if I do that for each of the equations, then I have t equals one thing, t equals another thing, t equals another thing. They should all be equal. And so the symmetric equations are setting those different representations equal to each other. Okay, so that explains where these 3 different representations come from. And the idea is that they each have value in specific applications. Now we're primarily going to focus on this vector equation, r equals r sub naught plus t times v. And really, we're going to use it to talk about this vector v. This vector v is going to give us the direction of the line. And it's really going to allow us to compare different lines together. So specifically, we're going to talk about determining whether lines are parallel, intersecting, or skew. And so here I have 2 lines, R1 and R2. And the first question is, are these lines potentially parallel? Well, the idea is parallel lines travel in the same direction. So all I have to do to tell if these lines are parallel is compare their direction vectors, v1, v2. Are those vectors equal? If they're equal, the lines are parallel. So I can do that by inspection here. R1 has a direction vector of 1, 0, 2. R2 has a direction vector of 2, negative 1, 1. Therefore, these ones are not parallel. Easy as that. Now, what about intersecting? Do these lines intersect? Well, intersecting lines share a common point. So that means they have to have the same x value, y value, and z value at some specific time. And so we might just try to compare their x components. We can distribute this t here, and think of this as t comma 0 to t. We can do the same thing for our other line, and this would be 3 plus 2t, and 0 minus t, and 1 plus t, like that. And so you might think, well, let's see when their x values match up. And so we might look at t equal to 3 plus 2t. The problem with this is not only saying do their x values match up, but really do their x values match up at the same time. When you've looked at parametric equations in the past, you understand that this parameter t, in some sense, is also talking about the time that we're at each point on this line. And so if we let both of these lines be represented by this parameter t, the same parameter, we're not only asking if they're going to be at the same point, but also at the same point at the same time. And that's not really what we're talking about with intersecting lines. We just want to know if they share a common point. So to adjust for that, we're going to let the first line be parameterized with t, and we'll just pick a different letter for the second parameterization. How about s? And so this statement is really saying, do they ever share the same x component? And we'll just do that for the other components as well. So we'll say, do their y components ever match? So this would be 0 equals negative s. Do their z components ever match? Is 2t ever equal to 1 plus s? Now we just go about solving these things. And so we're basically going to solve two of them to find certain values of s and t and see if it satisfies the last equation. So right away we know that if their y components are ever going to be the same, s has to be 0. So that is a given. We'll plug that into the first equation to get t equals 3. So the only way that their y components and their x components can ever both be the same would be if s is equal to 0 and t is equal to 3. And we plug those values into that last equation to see if, when they have that x and y value, do their z values also match up. We will get 2 times 3, which is 6, equal to 1 plus 0, which is 1. That's not true. So it looks like these lines do not intersect. There we go. And it might seem strange at first. We know that if they're parallel, they should not be intersecting, but these ones are not parallel. So doesn't that imply that they should intersect? Well, that might be true in 2-space, but not necessarily 3-space. So let me give you a quick 3-dimensional physical idea of why this is true. I'm going to draw the picture of a little house. So this is my little box-shaped house in 3 dimensions. Okay. And so now we can say this roof line right here, I could kind of extend that to think of that as a line in 3-space. But I could also look at the foundation of my house and draw a line along this edge of my house. And physically, thinking about this as a house, we know that those two lines are never going to intersect. But they're also clearly traveling in different directions, so they're also not parallel. And so lines that are neither parallel nor intersecting are called skew lines. And so how do we show skew lines? Well, we just go through the first 2 steps. We have shown that these 2 lines are not parallel, but they're also not intersecting. So therefore, these are skew lines. Okay, so now we've generated the different representations, different equations for our lines, and we've talked about really the physical meaning of the vector v. And that concludes this video. Thank you.